This video introduces the idea of theorems and also discusses some strategy for constructing proofs. Recall that in a proof, every line that is not an assumption in the main proof, a premise, or an assumption in a subproof must be justified by one of the rules. And we have 11 basic rules, a reiteration rule, and an introduction and an elimination rule for each of the logical connectives. We also have derived rules and replacement rules, which allow us to make certain moves more quickly. And we have this turnstile symbol that means that a proof is possible. For example, in the formula on the screen, it means that there's a proof where we assume C arrow D and D arrow E, and we prove C arrow E. It's also possible to use the turnstile symbol with nothing on the left-hand side. For example, show that it's provable that P or not P. This means we need to start a proof that doesn't have any assumptions in the main proof. That is, we need to start the proof without any premises at all. A sentence like this, one that you can prove without any assumptions in the main proof, is called a theorem. Our proof starts out like this. We get nothing to work with. Somehow, on some line, and I've just labeled it as n on the slide because we don't know what line that's going to be yet, we need to end up with P or not P. There are different possible approaches, but proving a theorem requires at least one subproof. That means using one of the rules that makes use of a subproof. And we have 4 of those. Conditional introduction, biconditional introduction, negation introduction, and negation elimination. Let's try a strategy using negation elimination. That means assuming the negation of what we want to show and proving an explicit contradiction. So that lets us start a subproof on line 1 where we say not P or not P. And now we get to look at line 1 and say, what could we do with that? Once we've started the subproof and made an assumption, we have something to work with. Looking at the rules, maybe you notice this rule, De Morgan. It's a famous set of equivalences named for the 19th century British logician Auguste De Morgan. So it's 2 replacement rules that allow us to convert conjunctions to disjunctions and shuffle around negations. The relevant version of De Morgan for our purpose is this one. If you have a negation in front of a disjunction, a negation in front of an or sentence, then you can replace it with a conjunction where you move the negation inside. So we have a negation of a disjunction on line 1, and De Morgan lets us rewrite the negated disjunction as the conjunction of 2 negations. That is, it lets us rewrite line 1 as line 2. You may want to look at De Morgan as it's written on the reference sheet and compare it to the version we're using on line 2 until you're satisfied that this is a legitimate application of the rule. But De Morgan allows us to take what's not very useful, this negated disjunction on line 1, and turn it into a conjunction. A conjunction is something we can use more readily because we can use conjunction elimination and elimination on line 2. That lets us write down not P by and elimination on line 2. It also lets us write down not P by and elimination on 2. Remember, we're inside a reductio subproof planning to apply negation elimination. So what we want is an explicit contradiction. And that's actually what we've gotten. Lines 3 and 4 here are a sentence, not P, followed by the negation of that sentence, not P. So line 3 and 4 gives us an explicit contradiction. That means we can close the subproof and apply negation elimination. So close the subproof, we write line 5, P or not P, negation elimination 1 through 4. Okay, that's a proof. We've proven the theorem. But suppose you didn't think to do an indirect proof. Suppose you didn't think of the negation elimination rule. You're looking at where you need to end up. You need to end up with P or not P. And looking over the rules of proof, you notice that there's this material conditional rule, abbreviated MC. It allows us to translate between disjunctions, or sentences, and conditionals, arrow sentences. And it's a replacement rule, so it can work in either direction. In this case, if we could get not P, arrow not P on the line just before the last line of the proof, if we could get it somehow, by material conditional, we could turn that into a disjunction. So I've written material conditional with a question mark because we don't know what line it's going to apply to yet, but it's going to apply to that line just before it, the conditional, not P, arrow not P. This is still thinking strategically about how the proof is going to end. But this idea changes our target. We now ask ourselves, how could we get that conditional? How could we get not P, arrow not P? Well, it's a conditional. So what about conditional introduction? So conditional introduction is one of those rules that calls for a subproof. So back on line 1, we want to start the right kind of subproof to apply conditional introduction. And it calls for a subproof where we assume the left-hand side, which is not P, and we want to end by proving the right-hand side, which is also not P. And I've drawn arrows here just to point out that one not P comes from the left-hand side of the conditional, it's the antecedent. The other one comes from the right-hand side. So we've started a subproof on line 1, we have not P, and in that subproof we want not P. It's easy enough. We can just reiterate line 1. And then we can finish with our plan. The subproof is complete after line 2, so we can apply conditional introduction to get not P, arrow not P. And that conditional introduction rule is applied to lines 1 through 2. It's applied to that subproof. It happens to just be 2 lines, but we're applying it to that whole subproof, the span of lines 1 through 2. And then the plan is, which we execute on line 4, we say, okay, from that conditional, we can get the disjunction, P or not P, using the material conditional rule. This is also a perfectly legitimate proof for the theorem. And the reason why I did it 2 different ways is to underscore an earlier lesson, that there are different ways to do any given proof. You should understand how both of those proofs work, because you should understand the rules and how they apply. But I won't ever ask you to prove something more than once. Some moves will seem more natural to you than others. Any proof that follows the rules and gets where it needs to go is just as legitimate and just as good as any other proof. So if you were given a problem on a homework or an exam that looked like that theorem we just did, either of those answers would have been perfectly good ones. Working through different proofs also helps to illustrate some general points of strategy. First, work forwards from what you have. When you have premises or things you've already proven, think about applying elimination rules to the sentences that are available to you. If you have a conjunction, the and/e rule lets you pull out either of the conjuncts. To work forward from a conditional, you need more. The arrow-e rule requires 2 lines. But when you've shown something in a proof or when you have something available, you should think about how you can work forward from that, what else you're allowed to write down. Second, work backwards from what you're trying to prove. Depending on what your conclusion is going to be, you can think about applying an introduction rule. Most proofs are going to require both working backwards, thinking where you need to end up, and working forwards, thinking about how you can get there from here. Third, if you don't see a way through, think about using replacement rules to rewrite sentences so that they're easier to deal with. The replacement rules are derived rules, so every proof that you can do using them is possible without them. But some proofs that seem really hard can be made easier by changing the symbols into other symbols with one of the replacement rules. Our use of De Morgan's and material conditional earlier are two examples of that. Finally, any proof can be done as an indirect proof. If all else fails, assume the opposite of what you want, derive a contradiction, and use one of the negation rules, either negation introduction or negation elimination. That's it. The rest is down to practice. To sum up, think in terms of these strategies. Given what you have, what else are you allowed to write down? Work forwards from what you've got. Given where you want to end up, how could you introduce that? What would let you write that down? Work backwards from what you want. If things get difficult, think about using replacement rules to rewrite things. And in the end, it's always an option to try an indirect proof and plan to use one of the negation rules.